Hello and welcome guys. Now in this video we will be implementing polynomial regression using both the methods. So first of all we will be implementing it using NumPy so that understand how it is different from linear regression, and then we will be implementing it with Scikit-learn. So let's do that. So first of all let's import NumPy as np, then import matplotlib .pyplot as plt. Okay, now what we will do, we'll generate synthetic data with a cubic relationship. So basically, why cubic relationship? Because we want our data to be non-linear. Okay, so for linear data we can use simple linear regression, but if it is non-linear relationship, then we have to use something called polynomial regression. So for that we are creating cubic relationship data. So first of all we need to set seed random dot seed 0. Okay, now x equal to 2 into np dot random dot rand 100,1. okay, then our y will be 0.5 multiplied by x cube minus 3 into x square okay plus 2 plus np dot random dot rand and 100,1. okay, so what's happening here is, so it's basically we are multiplying 0.5 into x cube minus 3x square plus 2 plus random 100. So basically what here it is doing, so it's generating an array with 100 random value which is uniformly distributed between 0 and 2. So the shape of x is 100,1, meaning that this is a column vector, and the y, so basically it's compute the corresponding based on cubic relationship with some added noise. So this is like a noise. okay, so 0.5 into x cube is the cubic term, then minus 3 into x square is a quadratic term, and then 2 into x is a it's a linear term. okay, so basically and then lastly the x is the linear you can say a constant term. okay, so now what we can do is we can write the polynomial regression function. okay, so let's create a function here, def polynomial regression, which takes x as the input, y as the input, and a degree. okay, so here it should be okay, 2 is missing here, I guess. okay, yeah. okay, so now our x and y is ready. Now let's write the code for polynomial regression. So x poly equal to npc of x, then for d in range of 2 comma degree plus 1, then we'll update the x poly again, which will be np dot x poly comma x square of d, which is the degree. okay, then let's update the theta equal to np dot linear algebra inverse algebra that we have to use here dot inverse, and here we have to pass our x polynomial transpose dot matrix of x poly. okay, then again dot matrix x poly dot transpose dot y. okay, now we have to return the theta, and so basically what we have done here is, so this x poly is we are initializing the polynomial features by creating a matrix, okay, which will contain the original feature x, and this is a matrix with power 1, or you can say linear term. Then we are running a loop. okay, so iterating over degree starting from 2 up to the specified degree, let's say 3, so it will run 3 times. So this loop generates additional polynomial feature for higher degree. okay, so then we are adding a column that to the x poly matrix, each representing high degree term of the original feature x. Then theta, so basically here we are computing the polynomial regression coefficient, which is theta, using the normal equation for linear regression applied to the augmented feature matrix. So this formula used here based on the closed form solution of linear regression, and then we are returning the calculated coefficient representing the parameter of polynomial regression. Now let's plot the polynomial fit. So for that, let's write again a function def plot polynomial fit, and here again x, y, theta and degree. Okay, so let's do plt.scatter, and here we'll pass our x and y and label. So label will be data. Okay, so let's create our x new, which will be np dot linspace 0, 2, 100. Now let's reshape -1, 1. Then we'll create x poly new, which will be np dot c of x new. Okay, now let's run a loop. So for d in range of 2, degree plus 1, here we'll update x poly new, x new to the power of degree. Okay, now y new equal to x poly new dot matrix of theta. Now let's plot it. Okay, so we are done with the polynomial fit function. Okay, let's run this. So what actually happening here is, so we are plotting the original data point x and y as a scatter plot, and then in this line we are generating a set of new x values evenly spaced between 0, 2 and for creating a smooth curve, and then we are creating a new variable x poly new. So here what we are doing, it is initializing the polynomial feature for new x value by creating a matrix called x poly new, and this contains the original feature of x new, and you can say this is a matrix with the power 1 linear term. Then we are running a loop. Okay, so here basically we are iterating over degree starting from 2 up to the specified degree, and this loop generate additional polynomial feature for higher degree for the x values. And then in the next line, what we are doing, we are adding a column to the x poly new matrix, and each representing a higher degree term of the original feature for the x values, and then we are computing the predicted value predicted y value for the new x values using the polynomial regression coefficient theta. And then we are plotting the polynomial fit curve using the new x values and the predicted y values, and the curve is labeled as polynomial degree. This is what we are here happening. So now let's plot the curve. So for that, first of all, what you need to define is the degree, right? Fit polynomial regression model with degree 3. Okay, so now degree equal to 3, then theta equal to polynomial regression, and here we will pass our x y and degree. Okay, now lastly we'll visualize the plot, and for that plot polynomial fit, and then again here we will pass our x, y, theta that we got from the previous step, and our degree. So let's run this. It's saying npc is not defined. Okay, it should be dot. X poly is not defined. Okay, okay, now let's restart the kernel, and I think the error shouldn't come. So it was here and x poly was not defined. Okay, so let's run everything again. Now you can see the beautiful plot. So this is the benefit of polynomial regression. So if we would have implemented this data using linear regression, the curve should be coming like this. Okay, and the goodness of polynomial regression is that you can see the balanced plot, and it has given a beautiful curve, which means that the model is perfectly doing great with this data using polynomial regression. And this is the advantage of using polynomial regression when we have data like this. Okay, or you can say non-linear data. Okay, so now let's do the same thing using scikit-learn, and we'll see how easy the implementation is. Okay, so let's do the using scikit-learn method. Okay, now for this we need to import a library, that is scikit-learn from scikit-learn dot linear model, import linear regression. Okay, and then from scikit-learn dot preprocessing, import polynomial features. Okay, so we are done with that, and we also have generated the dataset already. So what we need to do is we need to directly create the instance for polynomial regression. So so what we are doing here is we are transforming the features to include polynomial term up to degree 3. Okay, so let's do that. So poly features equal to polynomial features, and here we will pass our degree equal to 3 and include bias equal to false. Okay, and then now define x poly equal to poly features that we have defined in the previous step. Let's fit transform our x. Okay, now we need to fit a linear regression model to be to the transform feature. Okay, let's run this and fit the linear regression model to the transformed features. Okay, so linear regression equal to, let's create the instance, and linear regression dot fit x poly comma y. Okay, so this will fit the model. Now let's visualize the data and the polynomial fit. Okay, so for that x new equal to and p dot linspace 0 comma 2 comma 100 dot reshape minus 1 comma 1. Then we'll create x poly new poly features dot transform x new. Okay, now y new will be our linear regression dot predict x new poly. Okay, now let's run this, and we will have the prediction. Now let's plot the scatter plot. So plt dot scatter will pass our x and y original, and then we'll label equal to data. okay, and then plt dot plot. Here we'll pass our x new, y new, and label equal to degree 3 feet. Okay, so because we have done 3 feet degree here, okay, and that's why the label should be degree 3 feet. Okay, now the color should be, let's take it as a red. Then plt dot x label x, plt dot y label y, then plt dot legend, then plt dot show, and we are done. Okay, now you can see that similar plot we have plotted using the Scikit-learn library. Okay, and you can see that how easy it was. It was just 3-4 line additional to the existing numpy method. So that is what polynomial regression is, and this is how we implement. And you can see, right, I mean, how polynomial regression has advantage over normal linear regression. And just remember one thing, guys, in the real time you will won't have linearly separable data set. Okay, most of the time it will be non-linear data set, and you will have to use complex algorithm to solve those type of problem, because you need good fit, right? Your model shouldn't be overfitting or underfitting. Your fit should be very balanced. Okay, and that's why we use complex algorithm, and then polynomial is just an advanced version of linear regression. So hope you guys understood. Now see you in the next video. Thank you.